Good day, class. Before we start our lesson, let me introduce first myself. I am Mary Ann Reyes, your teacher in organic chemistry. So now, we will start our lesson. What is organic chemistry about? The term organic suggests that this branch of chemistry has something to do with organisms or living things. Originally, organic chemistry did deal only with substances obtained from living matter. Years ago, chemists spent much of their time extracting, purifying, and analyzing substances from animals and plants. They were motivated by a natural curiosity about living matter and also by the desire to obtain from nature ingredients for medicines, dyes, and other useful products. It gradually became clear that most compounds in plants and animals differ in several aspects from those that occur in living matter, such as minerals. In particular, most compounds in living matter are made up of the same few elements such as carbon, hydrogen, oxygen, nitrogen, and sometimes sulfur, phosphorus, and a few others. Carbon is virtually always present. So this fact led to our present definition that organic chemistry is the study of molecules that contain carbon compounds. This definition broadens the scope of the subject to include not only compounds from nature, but also synthetic compounds, which are invented by organic chemists and prepared in their laboratories. We all know, class, that organic chemistry are very important in our everyday life. It touches our daily lives. We are made of and surrounded by organic compounds. Almost all of the reactions in living matter involve organic compounds, and it is impossible to understand life, at least from the physical point of view, without knowing some organic chemistry. The major constituents of living matter are the proteins, carbohydrates, the lipids or the fats, the nucleic acid, which is the DNA, and the RNA, the cell membranes, enzymes, hormones. So these are inorganic, and we will describe their chemical structures when we go on our discussions. So these structures are quite complex. To understand them, we will first have to discuss simpler molecules. Other organic substances include the gasoline, oil, and tires for our cars, the clothing we wear, the wood for our furniture, the paper for our books, the medicines we take, and plastic containers, the camera film, perfume, carpeting, and fabrics. Name it, and the chances are good that it is organic. In daily, the paper, on the internet, or on television, we encounter references to polyethylene, explosives, styrofoam, nicotine, polyunsaturated fats, and cholesterol. So all of these terms refer to organic substances. In short, organic chemistry is more than just a branch of science for the professional chemist or for the student preparing to become a physician, a dentist, veterinarian, pharmacist, nurse, or agriculturist, and also a future educator. So it is part of our technological culture. Now, we will proceed to history of atoms, its theories, and model. All matter is made up of atoms. This is something we now take as a given, and one of the things you learn right back at the beginning of high school or secondary school chemistry classes. Despite this, our ideas about what an atom is are surprisingly recent, as little as 100 years ago. Scientists were still debating what exactly an atom looked like. and how they change over time. Now, through our graphic starts in the 1800s. The idea of atoms was around long before. In fact, we have to go all the way back to ancient Greece to find its genesis. The word atom actually comes from ancient Greek and roughly translates as indivisible. The ancient Greek theory has been credited to several different scholars, but is most often attributed to Democritus and his mentor Leucippus. Though their ideas about atoms were rudimentary compared to our concepts today, they outlined the idea that everything is made of atoms, invisible and indivisible spheres of matter of infinite type and number. So these scholars imagined atoms as varying in shape depending on the type of atom. They envisage iron atoms as having hooks which lock them together, explaining why iron was a solid at room temperature. Water atoms were smooth and slippery, explaining why water was a liquid at room temperature and could be poured. Though we now know that this is not the case, their ideas laid the foundations for future atomic models. It was a long wait, however, before these foundations were built upon. It was not until 1803 that the English chemist John Dalton started to develop a more scientific definition of atom. He drew on the ideas of the ancient Greeks in describing atoms as small, hard spheres that are indivisible, and that atoms of a given element are identical to each other. Now, Dalton's atomic theory proposed that all matter was composed of atoms, indivisible and indestructible building blocks. While all atoms of an element were identical, different elements had atoms of differing size and mass. However, since the neutron would not be discovered until 1932, we can probably forgive Dalton this oversight. He also came up with theories about how atoms combine to make compounds and also came up with the first set of chemical symbols for the known elements. Dalton's outlining of atomic theory was a start, but it still did not really tell us much about the nature of atoms themselves. What followed was another shorter lull where our knowledge of atoms did not progress all that much. There were some attempts to define what atoms might look like, such as Lord Kelvin's suggestion that they might have a vortex-like structure. But it was not until just after the turn of the 20th century that progress on elucidating atomic structure really started to pick up. The first breakthrough came in the late 1800s when English physicist John Joseph Thomson discovered that the atom was not an indivisible as previously claimed. So the plum pudding model, also known as Thomson's plum pudding model, is a historical, scientific model of the atoms. The plum pudding model is defined by electrons surrounded by a volume of positive charge, like negatively charged plums embedded in a positively charged pudding. So this is the structure of the model of Thomson's. So negatively charged is surrounded on the positively charged metal plates. From this, he deduced the rays must be negatively charged. By measuring the charge on the particles in the rays, he was able to deduce that they were 2,000 times lighter than hydrogen, and by changing the metal the cathode was made from, he could tell that these particles were present in many types of atoms. He had discovered the electrons, though he referred to it as a corpuscle, and shown that the atoms were not indivisible, but had smaller constituent parts. This discovery would win him a Nobel Prize in 1906. So in 1904, he put forward his model of the atom based on his findings. Dubbed the plum pudding model, though not by Thomson himself, it is envisaged the atom as a sphere of positive charge, with electrons dotted throughout like plums in a pudding. Scientists had started to peer into the atom's innards, but Thomson's model would not hang around for long, and it was one of his students that provided the evidence to consign it to history. So next, let's proceed to Ernest Rutherford. Ernest Rutherford was a physicist from New Zealand who studied at Cambridge University under Thomson. It was his later work at the University of Manchester which would provide further insights into the insides of an atom. This work came after he had already received a Nobel Prize in 1908 for his investigations into the chemistry of radioactive substances. Rutherford devised an experiment to probe atomic structure which involved firing positively charged particles at a thin sheet of gold foil. The alpha particles were so small they could pass through the gold foil, and according to Thomson's model, which shows the positive charge diffuse over the entire atom, they should do so with little or no deflection. By carrying out this experiment, he hoped be able to confirm Thomson's model, but he ended up doing exactly the opposite. So during the experiment, most of the alpha particles did pass through the foil with little or no deflection. However, a very small number of particles were deflected from their original paths at very large angles. This was completely unexpected, as Rutherford himself observed. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The only possible explanation was that the positive charge was not spread throughout the atom, but concentrated in a small dense center, the nucleus. As you can see on this model, the positively charged was concentrated at the nucleus and also the neutron, and most of the rest of the atom was simply empty space. Rutherford's discovery of the nucleus meant the atomic model needed a rethink. He proposed a model where the electrons orbit the positively charged nucleus. While this was an improvement on Thomson's model, it didn't explain what kept the electrons orbiting instead of simply spiraling into the nucleus. Next, Bohr model of the atom. Enter Niels Bohr. He was a Danish physicist who set about trying to solve the problems with Rutherford's model. He realized that classical physics could not properly explain what was going on at the atomic level. Instead, he invoked quantum theory to try and explain the arrangement of electrons. His model postulated the existence of energy levels or shells of electrons. Electrons could only be found in these specific energy levels. In other words, their energy was quantized and could not take just any value. Electrons could move between these energy levels, but had to do so by either absorbing or emitting energy. Now, Bohr's suggestion of stable energy levels addressed the problem of electrons spiraling into the nucleus to an extent, but not entirely. The exact reasons are little more complex than we're going to discuss here, because we're getting into the complex world of quantum mechanics, and as Bohr himself said, if quantum mechanics has not profoundly shocked you, you haven't understood it yet. In other words, it gets kind of weird. Bohr's model did not solve all the atomic model problems. It worked well for hydrogen atoms, but could not explain observations of heavier elements. It also violates the Heisenberg uncertainty principle, one of the cornerstones of quantum physics, which states we can't know both the exact position and momentum of an electron. Still, this principle was not postulated until several years Bohr proposed his model. Despite all this, Bohr's is probably still the model of the atom you're most familiar with, since it's often the one first introduced during high school or secondary school chemistry courses. It still has its uses too. It's quite handy for explaining chemical bonding and reactivity of some groups of elements at a simple level. At any rate, the model still required refining. At this point, many scientists were investigating and trying to develop the quantum model of the atom. Chief amongst these was Austrian physicist Erwin Schrödinger, and who you've probably heard of before. He's the guy with the cat and the box. In 1926, Schrödinger proposed that, rather than the electrons moving in fixed orbits or shells, the electrons behave as waves. This seems a little weird, but you probably already recall that light can behave as both a wave and a particle, what's known as a wave-particle duality. And it turns out electrons can too. So Schrödinger solved a series of mathematical equations to come up with a model for the distributions of electrons in an atom. His model shows the nucleus surrounding by clouds of electron in density, as you can see in our structure. So these clouds are clouds of probability. Though we don't know exactly where the electrons are, we know they're likely to be found in given regions of space. These regions of space are referred to as electron orbitals. It's perhaps understandable why high school chemistry lessons don't lead in straight with this model, though it's the accepted model today, because it takes a little more time to get your head around. So Schrodinger's was not quite the last word on the atom. In 1932, the English physicist James Chadwick, a student of Ernest Rutherford, discovered the existence of the neutron, completing our picture of the subatomic particles that make up an atom.